Hey YouTube, it's Brendan, helping you with another SAT problem that everyone seems to struggle with. This one, we're going to talk about the polynomial remainder theorem. So what the polynomial remainder theorem states is that if a polynomial, f of x, is divided by a linear polynomial, x minus a, then the remainder will be f of a. So what does that mean? Well, let's break it down sentence by sentence, word by word, phrase by phrase to get an idea. So if we have a polynomial, f of x just means a function. So this might be, let's just do something like f of x equals x squared plus 3x minus, 5. And then this is divided by a linear polynomial, x minus a. So let's say we took this and we divided it by, let's do x minus 3. So what we can see here is that x minus a is given by x minus 3. So this implies that a is equal to 3. Now what they're saying is that the remainder will be f of a in this formula. So if a is 3, the remainder should just be f of 3. Now, if you're not too good on functions, you might not remember that f of 3 just means the y value when you plug in 3 for x. So let's evaluate f of 3. So I'm just going to take 3 and I'm going to plug it in for x. So f of 3 is going to be 3 squared plus 3 times 3 minus 5. So that's going to be 9 plus 9 minus 5. So that's going to give us 13. So this is f of 3, and this is going to be the remainder when x squared plus 3x minus 5 is divided by x minus 3. Now, in the video before this, in the playlist, I talked about the polynomial long division, but in case you haven't seen that, let's show you the long way for doing this and show you how the remainder works out. So if we were to take x squared plus 3x minus 5 divided by x minus 3, this is what the setup would look like. We would put x squared plus 3x minus 5 inside of our division sign and x minus 3 on the outside. Now, step 1 is you have to divide. So how many times does x go into x squared? Well, x squared divided by x is just going to leave you with x. And then step 2 is you multiply. So x times x minus 3, we're multiplying this whole thing by this. And that's going to give us x squared minus 3x. Now the last thing we have to do is subtract. So I like to put parentheses around here to make it clear that I'm distributing the negative. And then I'm going to subtract these. So x squared minus x squared is 0. 3x minus negative 3x is 6x. And then finally, we bring down this negative 5. Now the next thing we have to do is divide again. So we just repeat this process. And we ask ourselves, how many times does x go into this 6x value? Well, the way that we do that is we're just saying, what is 6x divided by 6? Or 6x divided by x, and that's just going to be 6. So I put the 6 up here. Once again, I multiply this new term by x minus 3, and when I do that, I get 6x minus 18. The next step is to subtract, so I put a minus sign out here, and I subtract these two, so 6x minus 6x cancels. Negative 5 minus negative 15, well, that's going to give us 13. Now, x can't go into 13, so what does that mean? That means that 13 is our remainder. And we can see that this very nicely matches up with that initial result that we got. That f of 3 is equal to 13. And that's what the polynomial remainder theorem allows us to do. It allows us to figure out what the remainder is when f of x, a polynomial, is divided by a linear polynomial x minus a. But you can see that it's much quicker to go through the polynomial remainder theorem than it is to go over here and try to do this whole long division process. Let's go ahead and do one more. So let's say instead of f of x, I were to give you some function g of x. And we said that g of x is equal to 3x squared plus 5x minus, I don't know, let's go with 4. And I told you that this function is to be divided by x plus 2. Well, if we're dividing by x plus 2, what's a? Well, remember that this x plus 2 represents x minus a. So a would actually have to be negative 2, right? Because if I do x minus negative 2, that's going to turn into x plus 2. So from this, we see that a is negative 2. So the remainder is going to be g of negative 2, which would be 3 times negative 2 squared plus 5 times negative 2 minus 4. Negative 2 squared is 4. 4 times 3 is 12. So we'd have 12 minus 10 minus 4, which we're going to see is going to give us negative 2. So g of negative 2 just so happens to equal negative 2. And we can go ahead and verify that with the long division process. So x plus 2 is going to go on the outside. And then 3x squared plus 5x minus 4 is going to go on the inside. Now, step 1 is divide. So x goes into 3x squared 3x times. Then we're going to multiply. So x times 3x is 3x squared. 2 times 3x is 6x. We know the next step is to subtract. So I put a minus out here, and I go ahead and I subtract this. 3x squared minus 3x squared cancels. 5x minus 6x is negative x, and then we bring down the negative 4. We repeat that process. So how many times does x go into negative x? That's going to be negative 1 times. Once again, we're going to multiply, and we're going to get negative x minus 2 when we do that. And then we know we need to subtract. So here, when we subtract these two, negative x minus negative x cancels. Negative 4 minus negative 2 is going to be negative 2. Now, can x go into negative 2? It cannot. So we know the remainder is negative 2. And we can see very nicely, once again, that these two answer choices match up, that our remainder is negative 2, and that g of a is also negative 2. Finally, one last thing to note is that g of negative 2 equals negative 2 tells you a point that is on your graph. So every once in a while, the SAT will ask you to make a connection that goes a little bit beyond this first order one that we're making, and we'll ask you to connect this to a graph. So if g of negative 2 equals negative 2, that means that somewhere on your graph, the point negative 2, comma negative 2 must exist. Going up to this one, if f of 3 is equal to 13, then we know that the point 3, comma 13 must also exist on the graph. Thank you for watching. Hopefully this video clears up some of the questions that you had about the polynomial remainder theorem.